Hi, I'm Yuke Zhu, and today I'm going to talk about our recent work on imitation learning from video demonstrations. As you are watching this video from the workshop on imitation learning, I presume that we're all interested in how imitation learning can push the envelope of robot autonomy. Behavioral imitation has played an integral role in humans' cognitive intelligence and social development, and this is also a powerful family of computational tools for developing sophisticated robotic behavior that are hard to manually engineer. And imitation learning algorithms rely on human demonstration. So here I'm highlighting three main categories of methods for collecting such human demonstrations. And the first is kinesthetic teaching, where the human demonstrators physically guide the robot to perform a task and collect trajectory level information for learning. And this is showing you an example of trajectory learning method called dynamic movement primitives, developed by Stefan Shao and Peter Pastor on learning these primitives on a PR2 robot. And the second is teleoperation. Instead of physically guiding the robot here, a human can instead use external controllers to command the robot from a distance. And one example I'm showing you is the Robotics system that we recently developed that allows the user to use their mobile phone to connect to a robot through a cloud server so that by moving the phone in free space, it can control the anti-factor of the robot in 6 degrees of freedom. And the third is learning from passive observation. For example, by watching humans to perform a task and learn from these visual demonstrations. So this is showing one example of time contrastive network developed by Pierre Simonet and the other colleagues at Google, which proposed a method to learn from third-person demonstrations and imitate a policy on the robot. This work that I'm going to talk about today fall into the third category. So why this is an interesting problem, and there are many reasons why we are interested in imitation learning from visual demonstration. First of all, this just appears to me the most natural and the most human-like way of learning from demonstrations. And we as humans have the intrinsic ability to infer the goals and intents by watching other agents perform a task. This ability comes in the very early stage of baby's cognitive development. According to a seminal study by Andrew Methoff, babies as young as 14 to 24 months old is able to imitate demonstration from just the TV screen. And this is just a phenomenon only for babies and children. And we as adults routinely learn new skills and solving new tasks by learning from video demonstrations of other people. So now many people turn to online videos like YouTube to learn day-to-day activity like cooking and makeup. And there's also a bunch of technical reasons why we are interested in imitation from video and why this is a promising direction to enable large-scale imitation learning in a more realistic setting. First, it just gives us a great degree of flexibility to the demonstrators. They can now use their own body to perform the task demonstration, and they don't have to have any prior knowledge about the robot. And this kind of flexibility allows us to apply this imitation learning algorithms to robots with a high degree of freedom, where it might be very difficult to perform kinesthetic teaching or teleoperation. And more importantly, there's just a massive amount of video data available online. So if we want to achieve the ImageNet moment for big data imitation learning, this is really the promising direction to go. And in my today's talk, I'd like to highlight three of the key technical challenges in imitation learning from video demonstration. The first challenge is called compositional generalization. And I will talk about how we can develop a general imitation learning algorithm that can handle all different variations in task structure and task goals. The second is perceptual uncertainty. Since we are dealing with video demonstrations, we need to take into account the amount of uncertainty arising from imperfect perception models and how do we integrate this type of uncertainty directly in a planning-based formulation for imitation learning. And the third, I will talk about how can we achieve a stronger form of generalization to long horizon tasks, I will introduce you a new method that can train on a set of shorter demonstrations and extrapolate to longer ones that is never seen before. And finally, I will conclude this talk with some discussions on the open problems and open challenges in this problem domain. So in the past few years, we have been studying this problem on one-shot imitation learning from video demonstrations. We cast this as a meta-learning problem. The idea is to learn a meta policy that can look at one single shot of video demonstration of a task and instantiate a policy to perform the demonstrated task on the robot. So during training, we provide many training videos of different tasks, and the policy on the robot provides learning feedback to meta-train the model. During testing, we'll provide only a single shot of video demonstration of a new task, and this is a task that never appears in the training set. And we want the meta policy be able to parse the video demonstration and perform the new task shown in the demonstration. Several prior work have used end-to-end deep learning approach to tackle this problem, including one of our own called neural task programming, where the idea here is that the video demonstration can be used as a context to contextualize this meta policy so that it can specialize a certain task, so that we can get a task-specific policy that maps the current observation to the next action, conditional on the video demonstration. However, as you can see that this is quite a black box approach. It works well for simple and short horizon tasks. Often it needs a lot of data to train. So when the model goes wrong and we don't know how to fix it and how to improve that. So our idea is see if we can open the black box and infuse the model with more compositional model prior as the inductive biases in the model to improve the generalization. And one type of structure prior that has been extensively used in classic robotics is a task graph, which naturally captures the compositional structure of complex tasks and enjoy a high degree of human interpretability. But the problem is that most of these task graphs are usually manually defined and not compatible with deep learning. So the question here is how can we automatically construct this task graph from video demonstration, and how can we take advantage of this task graph in deep learning approach? This leads to one of our work called neural task graph, where we propose to use task graph as some kind of intermediate representations within the end-to-end trainable neural networks and that serve as some kind of relational inductive bias to capture the compositional structure of a task. So there are two key components in our NTG model. The first component is a task graph generator that takes a set of video demonstration as input and construct a neural task graph. And the task graph generator here is implemented as some kind of graph neural network. The second component is a task graph executor that look at the current observation and the task graph we just constructed and decides what is the next action to do. And this essentially gives us the policy. So one interesting technical detail I'd like to mention here is how do we represent the task graph within the network models. So the canonical form of task graph used in robotics have the nodes corresponding to the states and the edges corresponding to the actions that defines the transitions between the states. This representation becomes a bit problematic when the states are visual observations, where the state space becomes huge or combinatorial. Instead, we propose a conjugate form of task graph where we flip the nodes and edges. And in this case, the nodes correspond to the actions and the edges correspond a set of valid states that enable the transition to happen. And these are, in some sense, can be interpreted as the preconditions of the transitions. Now, because the action come from a finite set of high-level commands, and the graph have a fixed size, so it makes learning much more tractable. So once we construct this conjugate task graph, and during test time, when we have a new video demonstration, we first use a node localizer to map the current observation to a node on the graph. And then there's an edge classifier to decide what is the outgoing edge. And the end node of the outgoing edge tells us what is the next action to do. When we train the NTG model and we need to provide the action sequences that correspond to each of the video demonstration, and compared to prior work, and we don't need the hierarchical supervision of programming traces as used in one of our prior work called neural task programming. So this reduced the level of supervision needed to train the model. So to show you some results, on the left, I'm showing you one example where we first use virtual reality controllers to collect a video demonstration of a task. And we see that the model can successfully understand the task and sort objects from different categories into their corresponding bins. And compared to the prior work that doesn't utilize this type of compositional priors, we show that our NTG model with such structured prior generalize a lot better than the black box model and with less training data and weaker supervision. And we also show that our NTG model can be applied to real-world video datasets. So here is one example of using the NTG model in a real-world surgical robotic dataset called Jigsaw. And we show that our model is able to predict the task sequences from a single video and use the task graph generator to complete the graph by predicting the missing edges from the path. So NTG achieves the better compositional generalization and sample efficiency in training by infusing the deep learning models with these structured priors. And we're quite excited about this model, so we decided to perform more analysis on the model performance and the ability to generalize to new tasks. And we're able to see two sides of the coin. So for the first, the compositional inductive bias is really helpful for in-distribution task generalization. And by in-distribution, I mean that when the test tasks come from the same task distribution as the meta-training task, NTG learns to solve them very well. For example, in the block stacking domain, if we train the NTG model on many in configuration of block tower with 3 blocks, it effectively generalizes to other in configurations. But on the other hand, NTG is still quite data hungry. It needs over thousands of a training task on an 8-block stacking task to generalize well. And it performs poorly in extrapolation. So when the test task doesn't come from the training distribution, for example, training on block stacking with 3 blocks, but testing on 5, the performance degrades significantly. On the right is an experiment that we run on a block object collection task in Air2Soar, where we train on tasks with 6 and 12 steps. And we see that the success rate is below 5% when running on longer tasks of 15 steps. So from these experiments, we are kind of starting to ask us again, what kind of form of additional domain knowledge that we can inject to the model to achieve a stronger form of generalization? So one proposal come to our mind is a symbolic planner, which is widely used in a lot of classic robotics literature and have achieved strong performance in planning in very long horizon tasks. And a symbolic planner comes with a domain file that defines a set of like high level domain knowledge of the action preconditions and post effects in this problem domain. And it allows a model to perform planning without executing these actions using this type of domain knowledge. So we are asking ourselves, how can we integrate such domain knowledge from a symbolic planner to achieve a stronger generalization in the context of one-shot visual imitation? This is a technical question we investigated in one of our recent papers published in IROS last year. So in this work, we propose a planning-based formulation for one-shot visual imitation learning. And it is a two-stage approach. The first part, we use a symbol grounding network where we map the observation and also the video demonstration to a set of symbolic states. And in the second part, we use a symbolic planner that takes the grounded symbolic states and plan for the actions based on the domain knowledge. So let's first take a look at the symbol grounding problem. Here we want to map whatever the continuous observation and video demonstration to its corresponding symbolic states. So we use a symbol grounding network to make binary predictions of each logical predicate. One means the predicate holds truth, and the zero means that is false. And we use a modular design of the symbol grounding network to enable parameter sharing between the predicates. So first, we use object modules for each of them object. Intuitively, this type of object module extracts meaningful feature representation that are relevant to each object. And then the extracted object features are fed into a predicate module, which output a score between 0 to 1 for each of the predicates. As you might already see here, one potential problem of this symbol grounding is that we do not always get the correct result. For example, the model can very well have both high scores saying the block B is clear, nothing is on top of B, as well as saying block A is on top of block B. So this leads to some kind of inconsistency. And this type of noisy and continuous predictions are due to this intrinsic stochasticity and perceptual uncertainty in the deep learning models. As a result, there can be inconsistency if we just naively quantize the predictions by thresholding. And this inconsistency can also lead to subsequent planning failures, as the model cannot resolve the conflicts between the noisy predictions. So one idea is to perform a joint inference to clean all those inconsistency up. For example, we can use Markov logic network to infer the most probable states from a set of manually specified constraints in that domain. And once we clean up the symbols with a discrete symbol, and we can plug them into a classic symbolic planner to decide the action. But this approach requires additional human efforts to specify the constraint in that domain, and they do not scale up well with the number of predicates. So instead of doing this discretization, so we treat the output of the symbol grounding network directly as probabilistic symbols or distributions over possible symbolic states. This avoids the problem of invalid discretization, but this also requires a new form of planner that can directly deal with this continuous and probabilistic symbols. And to derive this continuous planner, and we need to first take a quick look at how a traditional classic planner on discrete symbol works. First, we have the state representation, which is in this discrete and symbolic form. And then we can select the applicable actions from the domain by looking at whatever the preconditions are satisfied so that the action can be taken at each step. And once we pick action, we can apply it to make changes to the current symbolic states and to lead to a new symbolic state. And finally, we can check if the goal is satisfied by checking the current symbolic state with the goal specification. So to operationalize the idea of having a continuous planner, we need to perform continuous relaxation for each of these 4 steps one by one individually. So for the state representation, instead of discretizing the network output with a threshold, we can use the probabilistic symbols to compute a distribution over all possible states. And we can compute the distribution score for each symbolic state by multiplying the score for each individual predicates together. And now we turn to applicable actions. Given a scene and environment like this, let's see if we want to apply an action of stacking B on top of A. In a symbolic way, we should check if this current state satisfies the precondition, like the block B is clear and also the robot is holding A. But now, instead, we can have a score for this action, which is computed by multiplying the score of all the predicates in the precondition. So the higher the score, that means the more likely the action is applicable. And once we select an action, we want to apply it to the score distribution. We derive a propagation rule on how the action application can make changes to the score distribution of all the symbolic states. And you can read more details about this in our paper, but just to give you a high-level idea of this approach, it is based on the current distribution, and there's no guarantee whether the actual states satisfy the precondition or not. So this leads to two cases. So first, in the case it might actually satisfy, and then the action can be executed. But the same distribution might also include uncertainty and errors from perception, so the execution might fail. So we need to consider both cases when adapting the distribution by action application. And finally, we have to check whether a state satisfies the goal or not. So rather than matching the predicates one by one with a goal specification, we can instead use some distance metrics to measure the distance between these two probabilistic distributions. So with these 4 steps of continuous relaxations of a discrete planar, we can now replace the symbolic planar used in our planning-based visual imitation learning models with this newly baked continuous planar that can directly work with probabilistic symbols. And these probabilistic symbols are predicted from the visual observation and also video demonstrations. So we test this new continuous planar in 2 domains, the same as our NTG work. One is block stacking, another is object sorting. So the yellow line shows the baseline results from the neural task graph. The green line shows a discrete symbolic planar by quantizing the symbols using Markov logic network. And the blue line is our continuous planar. And we show that by using this planar, it achieves very strong generalization results in both domains. And in particular, for the object sorting domain, and the baseline model has to see many different permutations of the task to be able to slowly learn the task structure of this sorting. We show that by using our continuous planar, it can quickly learn to sort objects by seeing only 8 permutations of objects, and it generalizes very well to alternative execution orders from very limited training data. So with 8 demonstrations, it can achieve 100% success rate on all possible permutations of object sorting. And this is due to the use of the domain knowledge in the planar. So this continuous planar work shed light on a very promising research direction on integrating deep learning approach with symbolic planning to achieve stronger generalization in visual imitation learning. And this work is directly inspired by 2 lines of research. One is the symbolic planar used in traditional AI literature, and they have been shown effective in long horizon reasoning, but they usually abstract away perception with predefined symbols and manually specify the planning domain. So there's quite amount of hand engineering and this part knowledge involved in designing this planar. The other is recent work on using end-to-end deep learning to plan from raw observation. This model directly operates on raw sensory data, but they usually only work well with short horizon tasks because making long horizon prediction with the model are typically difficult. So in the last I'm going to talk about one of our recent work on this direction, where the goal is to combine the best of both worlds. So I'm going to introduce a regression planning network that use some of the idea of regression planning and backward chaining in classic AI, but realize them with deep models so that it can perform long horizon planning directly on visual demonstrations and on visual observations. In contrast to classic symbolic planner, this method doesn't require planning domain, and it can directly operate on visual data. And in contrast to end-to-end learning to plan from observation, we can achieve much stronger generalization to long horizon tasks. So to motivate our approach, let's take an example of making this beautiful three-layer cake. So when we as humans make a plan to make such cake, we might think backward from the ultimate goal, where the high-level milestone, what are the high-level milestone we have to reach in order to achieve this goal. So first we have to make the base, and then the second layer, and then stack the top layer. These are the intermediate sub-goals to reach in order to make the cake eventually. And after we make plan for the milestones, we can plan our low-level actions to reach these milestone goals one by one. In this work, we developed a new hierarchical planning model called regression planning network that kind of simulate the idea of making this cake. So the model takes the current observation and the task goal as input, and it determines what is the next immediate sub-goal to reach. And the task goal here are specified by some symbolic expression. And you can think of them as some specification of the milestone goal and the final task goal. The key idea of this model is to iteratively plan backward. So the regression planning process is to apply the model recursively by feeding the predicted goal back to the model until a predicted goal is directly reachable from the current observation. And by reachable, we mean that this milestone or this sub-goal can be directly reached by one primitive skills of a low-level controller. The model first takes the final task goal and the current observation as input and predict the sub-goals that have to be done in order to reach the final goal. And we then use a reachability network to decide if the sub-goal is reachable. In this case, the reachability network says no here, so that means we have to plan backward even further. So in the next step, we feed the predicted goal from the previous step to the model again. The reachability network still says no. So that means this sub-goal is still out of reach from the current state by a single primitive call. And the process goes on and on until we reach a sub-goal that can be reached. Here, the reachability network says yes. So we stop planning here and execute the corresponding primitive skill controller. And this controller tries to reach the sub-goal from the current state. And after the skill execution is done, we can repeat the regression planning process again. So now let's zoom into this RPM model to see the inner working of this model. So first, we extract some object-centric scene graph from the observation that describe the object and their pairwise relationships. And using this object-centric scene graph, now given a final task goal, say we want to cook the cabbage and serve it as a dish on the plate. So there's two sub-goals to satisfy in order to complete the final task. The first is we have to cook the cabbage and also put the cabbage on the plate. So one of the key algorithm we use here is called sub-goal serialization. It determines the execution order of all these sub-goals in order to make sure that the plan does not undo some of the already achieved sub-goal. So this needs us to explicitly model the dependencies among the sub-goals using a dependency network. And we formulate the sub-goal serialization as a directed graph prediction problem among the sub-goals. So this is essential component in our model to learn to achieve compositional complex goal, as well as like generalizing to new goals. And once we determine what is the next immediate sub-goal, which is make the cabbage cooked in this case, and the reachability network determines whether this is reachable from the current state. Here we see that the reachability network says no, so we feed the preconditions of the sub-goal back to the network, and the preconditions are also predicted by the precondition network modules as a set of predicates. So here, to make the cabbage cooked, so we need to put the cabbage into the pot, have the pot on the stove, and also turn on the stove. So these are the set of preconditions have to satisfy in order to achieve this milestone goal. And finally, the reachability network says yes, which means the next immediate sub-goal of putting the pot on the stove can be directly reached by one pick and place action. So we execute the low-level controller to achieve this goal. So this kind of explains how the inner working of RPN looks like. So during training, and we use a large set of expert video demonstration that contains the visual observation, the demonstrator action, and the sub-goal as the supervision to train our model. And at test time, our model is tested on zero-shot generalization to new task goals that are not included in the training set. So here, the RPN model learns to plan based on the goal states without seeing any video demonstration of the final test task. Okay, so let me show you some results. We focus on evaluating compositional generalization of high-level plan here. We first use a great word domains to evaluate two types of generalization. The first is goal multiplicity. So we here use a door key environment where the color of the key and door shows the correspondence between the pairs. And we train a demonstration on opening only two doors and evaluating on tasks that open more than two doors. So we want to see if this model can extrapolate to this longer horizon tasks. And the second is plan composition, where we train our model on demonstration of subtasks, such as to get a key to open the door, as well as opening the door and reach a goal. But the model never see the complete task that compose these two subtasks together. And in the result, we show that the model is able to learn from the shorter task demonstrations and extrapolate to longer tasks, say opening doors, as well as like composing the subtasks together to complete the entire task of get the key, open the door, and reach the goal. And we also evaluate our model in a more interesting and more realistic 3D cooking environments, where we train our model on video demonstration of a cooking task with 3 ingredients and 2 dishes. And on the left, I'm showing you an example of a longer task with 3 ingredients and 3 dishes and 4 ingredients. So compared to prior work on learning to plan from observation, we show that the RPN can achieve nearly perfect success rate on this new and unseen longer tasks. Okay, so this concludes my main part of a talk on this 3 work. So just to have a quick summary here. So in this talk, I pinpoint 3 challenges in the problem of visual imitation learning. The first is compositional generalization. And I talk about our work on neural task graph, which use the task graph as some kind of structure inductive bias to generalize across different task structure and task goals. And then I talk about how can we address the perceptual uncertainty from the deep learning-based perception models when parsing these video demonstrations into symbols. And I introduce a way to perform continuous relaxation of a symbolic planner for one-shot imitation learning in a planning-based formulation. And last, I introduced regression planning network, a hybrid model that uses the ideas of regression planning and backward chaining in classic symbolic AI with deep learning-based models to achieve extrapolation to longer tasks. And this is the work done with my amazing collaborators, Dian Huang, Danfei Xu, and Suraj Nair. So since this workshop talks about both the advances and also challenges in imitation learning, so I'd like to conclude my talk finally by pinpointing some of the open challenges and problems in scaling up today's visual imitation learning model to the next level. Clearly, there's a lot of open challenges waiting us to solve. So the first, the kind of computer vision machinery, as you can see we're using here to process this video demonstration are still quite simplistic. Our model works well on highly structured video demonstration in restrictive domains. But to apply these methods to real-world web videos, we need more advanced video processing and activity recognition methods from computer vision to be able to extract more meaningful procedural knowledge from unconstrained video data in order to achieve our dream of learning from YouTube to cook or install IKEA furnitures. So second, our method assumes that there's already exists a vocabulary of discrete symbols in the visual concept. So far, these symbols are manually defined for each domain individually one by one, and they are defined a priori. This is certainly not a scalable approach in the wild. So is there a way that we can automatically acquire these symbols and concepts? I think it would be very interesting to look into concept learning and symbol discovery methods that can learn and acquire such concepts directly from robots' self-exploration in the environment in a lifelong fashion. And last, we have seen the power of integrating the representational power of deep neural network, as well as the generalization power of symbolic reasoning. I think this is really a very promising direction to go to on how to build the next generation of hybrid imitation learning method that can seamlessly integrate the strengths in the both two paradigm of learning. And with that, I'd like to conclude my talk and thank you.